So anyway, that'll be Friday. It'll be better.
What's Friday?
I just told everybody to come to class Friday. So
Is it like?
I don't know. I just told everybody to come to class Friday. I don't know what that means, but I told everybody to come to class Friday.
Should I continue studying for Friday?
I don't know. I just told everybody to come to class Friday. I tell everybody to study all the time, so I mean, I wouldn't be inconsistent by telling you to keep studying.
I remember for Calc 1, you forgot to give us the delta epsilon proof.
Delta, and then you just gave it
You gave us the second test. The day after. And everybody, because the one girl, I forget what her name was, she was like, after she took that test, I heard her go in the hallway, she's like, thank goodness there was no epsilon delta. And I remember her walking the next day, she had just got in the classroom and you were handed those out, and she's like, she was like almost in the verge of tears. I forget what her name is. She's still here. I never knew her name.
That's amazing. That's almost as precious as a person crying after my Calculus 3 tests. It made me so happy. No, it doesn't actually make me happy. I'm a terrible person.
Sadistic math tests.
Yeah, I'm a terrible person. I ask people actual questions about math.
Try not to judge my lineage too hard, else I might cry.
Oh, let's begin with a prayer. Dear Heavenly Father, we thank you for this day. Just pray you'd help us to learn a little bit more about whatever it is we're learning. In my prayer, in Jesus. Amen. All right, so these are things I wrote like 10 years ago or something. I think this is my thesis. I don't know. It looks like something I wrote. It's been a while. So let me give you a rundown of what we're going to do. So basically, I'm just going to try to give you a crash course in Supermath. So what is Supermath? So, well, there's various kinds of Supermath. The kind of Supermath that I endorse and practice is, I would say, I don't know, in my view, a relatively unsophisticated sort. The idea is essentially this, is you just replace numbers with supernumbers. So numbers, in the traditional sense, would be like real numbers, complex numbers, rational numbers, whatever. But you see, numbers have some pretty usual properties. For example, they commute. They commute. They, you can't multiply two of them together and get 0 unless they're both 0. Well, okay. That kind of depends on what you mean by number. There is another generalized sense of number where you have 0 divisors as well. But supernumbers, I guess the main feature of supernumbers is they have what's called a Z2 grading. And what that means essentially is that there's even supernumbers and there's odd supernumbers. So, terminology. You got even numbers, you got odd numbers. All right. The even supernumbers are also commuting. They're commuting. The odd supernumbers are anti-commuting. So yeah, it's a departure from commutivity, but not too far either, because you can always write a supernumber as a sum of an even supernumber and an odd supernumber, where the piece which doesn't commute just anti-commutes, which means a times b is equal to minus b times a. So it's kind of a skew symmetry condition. Evens commuting, odds. Now there's other more physicsy terminology. Sometimes you might think of something like this as, generically speaking, bosonic, whereas this sort of thing is fermionic. So, that's kind of the big picture, is that we want to replace numbers with supernumbers. As a point of motivation, right, just to explain to you briefly where these things came from. Maybe the late 50s, something like that, people were studying something called the path integral. And Berezin, I think it was, introduced anti-commuting coordinates in order to model fermions in the path integral. And so, like physicists tend to do, he just said, well, suppose you've got this coordinate that's not like a regular coordinate. Suppose it doesn't commute, it anti-commutes, And he worked on it, and they derived various properties like the way it changes under coordinates happens to be inverse to the way the commuting variables transform, and so that gives a needed cancellation in something called a, I believe, path integral. And so, that kind of got the ball rolling, I should say. I mean, there you already had it. You had these commuting and anti-commuting variables, and I mean, physicists just started using them. And then by the early 70s, you had the birth of, you call it a hadronic string theory. People were first studying string theory as a theory to describe quarks and such. Because there's just, the thing about quarks is you can't like, they're confined. You can't observe a quark just sitting out on its lonesome. They're somehow like glued to the nucleus by these gluons. And so one like sort of just heuristic idea was that they were connected with strings. Something like that. And people still work in these kinds of things. I don't know too much about that. Anyway, long story short, in the early 70s, this work in hadronic string theory very soon morphed into what was the birth of what we now know as superstring theory and so forth. And just the nature of that topic involves the study of both commuting and anti-commuting things to describe bosons and fermions. So that's kind of a natural place to generate interest in this kind of math. But separate from that, and in parallel to that, people also were studying what's possible in terms of physically reasonable formulas that represent the Poincare group. And if you just use Lie algebras, you can only get certain, but you have certain features like, just basically interactions are not allowed between objects that have different spin. So there's no way like traditional symmetry groups could change something with spin 1/2 into something with spin 1, or things like that. There wouldn't be rotations in these abstract symmetry groups between things of different Poincare type. But the thing is, if you enlarge what's possible a little bit and you relax Lie algebras and you, instead of allowing Lie algebras, allow what are called super Lie algebras, then you're able to add these generators which are themselves spinners, and these things actually will mix different representations of the Poincare group. So you end up finding this way of having symmetry groups which rotate bosons into fermions and vice versa, and so you get these things called super partners. For the electron, there's a corresponding selectron. For the photon, there's a photino, and so forth and so on. And so that, roughly speaking, that was born from this no-go theorem, maybe 68 or 69 of Haag, how was it? Coleman-Mandula, the Coleman-Mandula paper. That was the no-go paper, and then the corresponding, hey, actually we can go if we relax it a little bit, was by 3 other authors I forget the name of. And so that was the birth of supersymmetry, which is a slight extension of the Poincare group. Like the Poincare group is space-time translations and Lorentz transformations. Basically, you've got the velocity boosts and rotations; those make up the Lorentz group, and then you have space-time translations. The semi-direct product of those two things makes up the so-called Poincare group. Just like the group of rigid motions is the semi-direct product of ordinary translations and ordinary rotations. In the same sense, you can talk about, and you can formalize this. You can talk about something called Minkowski space, which takes as its group of rigid motions things that are in the Poincare group. In contrast, the Euclidean space is something which takes as its group of rigid motions, the usual rigid motions. So there's a very parallel theory of geometry. Anyway, getting beyond that, there's a super Poincare group, which adds, in addition to boosts, rotations, and spacetime translations, it adds these two new generators, or I forget how you count, don't ask me to count, but it adds a couple of spinor generators, which have the potential to mix different representation types, which is interesting and new and bizarre. And then if you study the representation more carefully, it turns out if you want to do that reasonably, you can either look at n equals 1, 2, 3, or 4. Although I have seen papers with n equals 8, so I'm not sure what that's about. But what's possible in terms of enlarging to super Poincare algebras is somewhat, there's some structure there you have to deal with. Anyway, so the birth of the super Poincare group and then corresponding spaces to represent it, this is all like happening in theoretical physics in the 1970s. Ultimately leading to the local version of that. If you have the super Poincare group locally implemented as a local gauge theory, it gives rise to what's called supergravity. There's a similar sense in which the localization of the Poincare group gives rise to general relativity as a local gauge theory, like we were talking about. That's not like we were talking about, actually. Anyway, you can tie it into gauge theory if you have time. So, anyway, supergravity then gave way to what was then called superstring theory. Something called the anomaly problem was solved by Witten in like '84. That was a big deal. And then there's just been revolution after revolution after revolution in superstring theory since that time. But it's all in terms of studying I mean, basically, as I understand it, pretty much anything we can do in string theory, if the calculations are going to be doable, they're doable in some sort of supersymmetric context. I mean, as I understand it, if you try to do string theory without supersymmetry, it's really, really difficult, and we can't do much. Anyway, I won't try to explain what string theory is or anything, but just to let you know, string theory has a discussion of bosonic and fermionic variables throughout it. I mean, it's just there. And so supermath, generally speaking, is the kind of math you need to treat bosons and fermions in the same sort of level playing field. At the same time, I will warn you, I will confess, that the kind of supermath I'm describing to you right now is not I mean, there's a sophisticated sort of, well, in my view it's sophisticated because I don't understand it that deeply. I don't know if that really makes it sophisticated or if it just makes me ignorant. But you know, there's another kind of way you can do supermath using algebraic geometry, modern algebraic geometry, where what you do is you replace the sheaf of smooth functions with a sheaf of commuting functions, because they're ordinary functions, with like anti-commuting with more exotic functions or something like that. And so everything is done with these modern algebraic geometric techniques, sheaf theory and such. And I have yet to be successful in teaching undergraduates sheaf theory, so it's kind of, I mean, I could try to do it that way, but then I would have to wait till you guys were in like your 6th or 7th year here, and by then I would hope you were in here. So I kind of like the direction my thesis went, because this kind of supermath is much more accessible to undergraduates. Because really, once we get the ball rolling here, what you're going to see is what we're doing is just doing what you've already done, replacing real numbers with supernumbers. And just sort of naturally generalizing usual point set theoretic definitions. Now, I guess, broadly speaking, that puts us in the camp of analysts who think about points as being basic, as opposed to that other crowd who thinks about sheafs or functions as being basic. The other crowd will eventually win, but us naive point-loving folks can enjoy our day in the sun. Or, anyway, it's what I know. I would like to learn the other way of doing things.
I mean, wasn't it in advanced calc we kind of thought as functions as kind of basic things, or kind of treated as like constants almost?
Yes, but it's worse than that.
Worse than that.
It's worse. I can't. I'm being fuzzy. All right, so supernumbers. So let me just try to be brief and tell you what supernumbers are as quickly as I can. My thesis in our work began by studying Alice Rogers' work. And she has a good book written relatively recently, Supermanifold Theory and Applications, where she describes her way of doing it. My way of doing it is a little bit different. It's more in tune with Bryce DeWitt's Supermanifolds book, which is a little bit old now, I guess. But and then I also spent a lot of time thinking about Bookbinder and Kuzenko's ideas and methods of supersymmetry and supergravity. That was another thing I did think a lot about. Double-sided. If I only do the, I think this would be difficult if I just do the even pages. All right, so just a little notation, real briefly. I will denote like z sub I. This I is going to be something like a multi-index. And so that's actually like z I1, I2, ik sometimes. And this is, so I'll say I is an element of ik, k greater than or equal to 1. And, all right. There's also the case that at the bottom of everything, I guess I'll write it over here. At the bottom of everything, I also have like zi equals to z naught. There's that's sort of the base case. Just the first thing, just a one thing. Now, this is an infinite set. I'm not saying that these are just indices of length k. So I mean that could be, you could have like a million, 1,000,001, 1,000,002, Trump's net worth. I mean whatever. You know, these are just indices. I think they have to be. We do assume that they're increasing. Okay. All right. So those are going to be coefficients. I will typically take them to be complex numbers. All right. The generators then. So these are coefficients, notation for coefficients. Oh man, this is that symbol. You know what I'm going to do? I'm going to ignore my thesis and change. I do better if I use Bookbinder's notation. So I'm going to use, oh, I don't know. You know what, let me just try to learn this, write this symbol. This thing. What is this called? Oh, I just can't do it. If I'm going to write 300 of these today, I can't do it. It'll slow me down. It'll eventually become, if I'm not typing.
Call Pac-Man.
Call Pac-Man. That'd be obnoxious. I can't use A to I and A to J.
You found Oopsilon, now you can find Oopsicron.
Ooh, Oopsicron.
Remember that joke when you're grading my test?
Wait, what is it?
Oh, well, I had discovered, you know, I've recently discovered that I like this symbol again. I think I knew it before, but I think it's a cool symbol. My wife said that she had a professor who liked to use it because he said it reminded him of trees.
Yeah,
That's what I was
like a
gonna
palm
say.
tree.
Palm
It's
tree.
like a tree, and then I told Lorenzo it was Oopsilon, and she's like, oh, that's like Epsilon, but you made a mistake. Thanks, Lorenzo. Oh, for those who don't know, Lorenzo is Lauren from zoology. I guess I should mention that for the larger audience. Some of my best students are not math majors, as it happens. It's weird, but I think the biology students here are the most academic of anybody. Like, they're the most broad in their interests, as far as I've observed.
It's because biology's not enough. Math is enough, biology's not enough.
Because biology's not enough?
That's a good,
Fantastic,
that's a good
Daniel.
argument.
That is almost on par with your relabeling of applied calculus as almost calculus, which I believe is a succinct and powerful way of describing the course.
They don't even call it applied, it's called business, doesn't it?
It is technically applied calculus for the business and life sciences. I also am fond of my brother's description of it, calculus with a trig lobotomy. It's also a useful description. My wife's comment about it is, my high school calculus was much harder than this.
Mine was. I
Why
remember
is
that.
why is it just polynomials and why are people still having trouble with it? It's just polynomials. It's like, I don't know. I shouldn't really record these things so well. I'll edit it out later. No, I won't. It's here. All right. So these. Oh, okay. So this would be analogous. It would be an analog. An analog of this would be like I squared equals to -1. So these things that anti-commute, these are the so-called Grassmann generators. And so I told you that the history of this starts with Berezin and theoretical physicists of the mid-50s to early 60s. Not entirely accurate. I mean, Grassmann, who was, when was Grassmann active? It was a while before that, like 1840s.
Okay.
So, yeah, Grassmann was looking at these kinds of algebras a long time ago. But maybe not infinite dimensional ones, right? Maybe just finite dimensional ones. See here, I just suppose you have as many of these as you want to play with. It just goes on and on and on. You can have as many of them as you like, right? You can ask, how would you construct such generators? How do you know such things exist? And I would say the answer is given to you by abstract algebra, and I will leave it at that. Okay, one of the things we can immediately see is if we have any Grassmann generator, right? And you look at it with itself, anytime a Grassmann generator is repeated, since it anti-commutes, that tells us that a to I squared equals 0. All right. And we also assume that these Grassmann generators are linearly independent over the field we're working. So, like, it's not possible to have some linear dependence between the Grassmann generators once we look at sums of them.
Kind of like the wedge product.
Yeah, it's a lot. And yes, there are connections between this and the wedge product. That is true. Don't ask me to make that explicit, though, please. K equals 0 to infinity. So here's like a little bit greedier version of that linear independence I was just talking about. Ci1, Ik, a to I1, a to I2, a to Ik equals to 0 implies
Each of the coefficients is equal to 0.
exactly. And I suppose at the moment, since I haven't introduced any notion of convergence, I'm assuming we're working with polynomials, so like finitely many of these are non-zero. I'm just writing it in infinite. I mean, this is... Oh. Oh my. It's worse. You guys, it's worse than you think. It's so much worse than you realize at the moment. You do realize that for each value of k, I'm taking a sum over the repeated indices.
Oh, yeah, right. So it's like a sum of k sums. So it's an instant sum of sums.
Yeah, but these indices not being limited to any finite range are also, yes, it is a infinite series of infinite series. Yes, but that's not too bad if you assume that only finitely many of these are non-zero. There's no issue with convergence still. It's just a convenient notation for a very big space. Now, we will assume that the coefficients are antisymmetric, just in case we want to work with indices which are also not increasing. Like sometimes it's convenient to look at expressions which just allow like 1, 2, and 2, 1. So if we do that, then we'll assume that the coefficients are antisymmetric, as to not get confused. All right, anyway, enough about that. You can also rewrite this in a more compact notation as follows, and this is sometimes useful. Sorry guys if I'm telling you stuff that doesn't matter too much to us. Oh, stink. The first sum is just multi-indices over the set of k indices. Again, that's an infinite set. But these are those kinds of things, and then the sum k equals 0 to infinity, like that. Let me kind of unwrap this a little bit. What this means, all right, explicitly, is C0, the first term. That's the 0th index. And instead of writing C, let me just write Z and get to the point here. Z. So this would be Z equals to that. So you have the Z naught, and then you've got plus the just one index. You could also write like this, right? Zi, eta I. And then you could write, and we put 1/2 Zi, j, eta I, eta j. I think here, these are not assumed to be increasing in sums. These are just sums over all possible values of I and j. So like here you could have 1, 2, or 2, 1, and that's why there's a 2 there, and that's why there's a 3 factorial in the next one. And, okay, so if you allow these Grassmann generators to be taken from, like, for arbitrarily large indices, I would say it's infinitely generated, right? On the other hand, if you just say, okay, we're just going to work with n Grassmann generators, okay? And, I mean, one nice reason to do that is then you could actually explicitly implement it as matrices of a certain size, right? You can make Grassmann generators with matrices. You can generate this algebraic structure using matrix multiplication of particular matrices. So in the finitely generated case, I would call it something like lambda n, built from, you know, just eta 1, eta 2, eta n. So if that's the kind of supernumber you're working with, that's not infinite. There's like finitely many supernumbers, because anytime you have a generator repeated, game over at 0. So basically, these ones either look like, so you got like Z naught at the bottom, then you have degree 1 stuff, which would be like Z1 eta 1, Zn eta n, right? Yeah, stuff like that. Then you've got stuff that's order 2, something like Z1 2, eta 1, eta 2, and then so forth and so on, however you want to order them. I'll just do it this way. Zn minus 1 n, eta n minus 1, eta n, right? Degree 0, degree 1. This would be degree 2. And I'm talking about Grassmann degree. Well, you keep going on, right? Eventually, you get to Z1, 2, n, eta 1, eta 2, eta n. And here's where I really like your comment, Jess. This is a lot like wedge products. That anti-commuting property is so much like wedge products, in fact, yes. So, like, past this, right? If you have form degree larger than n plus 1, what has to happen is you have to have one of these Grassmann generators repeated.
So it's 0.
Right, so it gives us 0. So, in fact, I mean, you could do the counting. I don't feel like doing that at the moment, but the dimension of the space of this, over, if you're taking coefficients from some field k, the k dimension of this, of course, is less than infinity. I mean, it's whatever that is. Ask a combinatorialist. It might just be 2 to the n, though. I'm not sure. Is it the same as wedge products?
It looks like that.
Okay, so these things we're looking at right now, these are supernumbers. Supernumbers are linear combinations of Grassmann generators. So when I say it's simple, it's just simple. You just replace the number with a supernumber. Many students would disagree with me. See, that doesn't seem that simple at all. Well, whatever. It is nevertheless something concrete. You can actually explicitly build these Grassmann generators through. I mean, there is a way of showing such objects exist which do have these properties. Okay, I'm not going to do it, but you can do that. It is something you can do. Okay, so in contrast, if you can get back over here, this world of infinitely generated supernumbers, this doesn't have to terminate, right? And even if it did, any one of these could include infinitely many terms, because you can have, you don't ever run out of generators to three-peat. You got infinitely many different distinct three-peatings, infinitely many three-peatings. Yes. Okay. Yes. Peat. No, peat-peatings.
Pete in the repeat.
Peat
In the three-peat.
No.
Never mind.
Uh-oh.
Ignore it.
Okay, so a little more fun terminology, and I think this terminology is due to what I think it originates with DeWitt. Man, do I have his book in here? I might have left that one home. Not sure. Anyway, this and this are sometimes denoted Z sub S and Z sub B. Care to guess what the B and the S are for? It's not Barbra Streisand.
Oh.
Is S like the super part? Or?
That would seem like a reasonable suspicion. Keep guessing.
Is the B the base?
That would also be a reasonable term, but no.
Boring.
Beginning?
Is B boring?
Another reasonable term, but no.
No. Okay.
What's up?
I said boring.
Boring? No, it's not boring. Yeah. Thank you, Daniel. Other Daniel.
Yes.
Look at him.
Is it English?
It is English.
Okay.
Here, once I give you one of them, tell me if you can get the other one.
Yes. Body and soul.
Body.
Yeah. He calls this the body of the supernumber, and the other part's the soul. This is the ethereal part. This is the ordinary element of the field that you're working over.
Pretty creative.
So ridiculous.
It's awful. You can read papers, rather serious papers about searches, like a search for ectoplasm, and in some sense I think it has to do with searching for things that have this kind of stuff, roughly speaking. But anyway, I could be all wrong about that. I'm not an expert in ectoplasm. But who you gonna call? I don't know. Okay, so listen. There's another way you can slice and dice this thing. You can break this up into like this: Z0 plus 1/2 Zij eta I eta j plus dot 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 dot, and then plus Zi eta I plus whatever 3 factorial Z ijk eta I eta j eta k plus dot 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 dot. So, you can prove this is a so-called even supernumber. This is a so-called odd supernumber. You can talk about the even piece and the odd piece of Z. And if you have a number which has just got an even piece, it's called an even supernumber, or a commuting supernumber, which is a good description of it. It commutes with everything. If you have an odd supernumber, it does not commute with everything, but it does anti-commute with other odd supernumbers, and it commutes with commuting numbers. Something that has non-trivial even and odd parts, sometimes called inhomogeneous. But we have the nicest formulas for homogeneous supernumbers, supernumbers which are either even or odd, but not a sum of both. All right. Sorry, I have a lot to say about supernumbers. I'm not sure we're going to get to anything else interesting today. And I'm not sure that's wise. I think maybe I should find a faster path through this so I can get to the interesting stuff, because I think I might care more about supernumbers than most people. All right. So nothing has been said about, I've been basically assuming, setting aside at least questions of convergence. I mean, I've been assuming that only finitely many of these are non-zero for the sake of logic. But in fact, you can, you know, you can also add infinitely many non-zeros if we give us also some notion of convergence. So we don't even need to do that yet, though. You can still at least talk about the algebraic structure of these polynomials, essentially. And so here are some fun, basically, here's the multiplicative structure. Let me talk about multiplicative structure here of the algebraically, let's see here, I call it, I have a variety of annoying and obtuse notations for these things. So here, what I mean by that is they're infinitely generated, but I'm only considering questions of algebra. In other words, I haven't committed to a particular notion of norm yet. So if you like, I'm really assuming that, well, anyway, let me shut up. So first of all, equality. Z is equal to W. That's true, so like you can expand it. That means the sum P equals 0 to infinity. The sum I element of the P indices, Zi, A to I, that's a multi-index, and a product of P Grassmann generators at each level. P going from 0 to as many as you like. And again, I'm setting aside issues of convergence for a second here, but A equals 0 to infinity, sum over I an element of the P indices, Wi, A to I. All right, so that's just expanding it. And then by linear independence of the generators that we're assuming, it immediately pops out if you got Zi is equal to Wi, right? For all I in like 0 and I1 and I2 and so forth and so on. I'm not sure that's quite the right way to write that. Maybe I should just say, maybe just say what oh, that's why I invented that notation. Not me, probably my advisor. For all I in, look, here's an awful symbol. This is the set of all possible multi-indices taken from infinitely many things of arbitrary length. There's all the indices you could ever hope to need, countably speaking, of course. Also, now this is pretty cool, you can multiply them. And so I suppose, I guess this is a definition in some regard. How do you multiply supernumbers, right? You could probably, if I had constructed these from something else more basic, right? If we'd actually constructed these from something else more basic, you could see the multiplication I'm about to write down is just some sort of facet of that construction. But really, it's just part of the definition. We assume that you can multiply them and the usual distributive properties go through. It's kind of just like sometimes when I'm teaching complex, I say, well, complex number is just, you take two real numbers, you put an I next to one of them, and then you just, like usual, that distributes and multiplies, you can commute them and go down, right? I mean, I have to drop that commuting statement here, but the distribution is just the same. And here's how that goes. So if I'm so foolish as to try to multiply two of these things, here's what it looks like. Z times W, you're like, what, you're going to multiply two infinite series of sums of Grassmann generators. Yes, I am. And I'm introducing another notation, which is what I tend to do. If you don't pay attention for 2 seconds, I'll have changed my notation because that's just how we roll. Now, this ZP, that would be like this whole thing is ZP, right? This whole thing would be like the WP. It's the degree P. It's the degree P piece of the supernumber. It's the supernumbers built with P Grassmann generators. It is a thing. So, okay, so what do? This is basically, by definition, P equals 0 to infinity, some R equals 0 to infinity, ZP, WR. I gotta be careful about the ordering of things here. And then you just now break it back down into the more basic level of things. So this is the sum P equals 0 to infinity, some R equals 0 to infinity, some multi-index I from the P indices, sum over the J from the R indices, and then what? Then you got yourself a Z sub I, a W sub J, and then eta I, eta J. Again, if you read my, and I think I can give you guys a link to this thing, if I can find it. So this is what I have in my, I think my thesis. I think this is my, it's either my thesis or, I'm not sure what this is. Maybe it's, I was trying to write a book. Not really to publish, but just, you know, for myself. I used, so this, in my notes, you'll see this thing. This is what I can write. Fast. All right. Now, this isn't quite the right presentation, you see, because we want to put these in order, so to speak. So you have to commute. Like if this has, I want to put them in order of increasing indices. So, otherwise I don't have a proper Grassmann expansion. Like this formalism. This formalism assumes increasing indices. In contrast, this one does not. We saw this when we studied advanced calculus, right? We could either write like the Faraday tensor in terms of like just the form basis with like dx1 wedge dx2, d2 wedge dx3, d1 wedge dx3. Although we usually use dx3 wedge dx1, so it's like z kind of, sort of. But or you could just do a sum over 1, 2, 1, 3, 2, 3, you know, all possible indices, 2, 1, 3, 1. There's and just it's just a combinatorial factor, and you have anti-symmetry of the coefficients, so it's all the same. It's a question of whether you want to look at sums over increasing indices over all indices. These are options that you have, and sometimes one is better than the other. Anyway, so here I have to pay the price of increasing indices. These aren't necessarily increasing, right? So what you do is you just reorder them. And doing that generates a sign, plus or minus 1. And these aren't changing. I'm just going to write them like that. Okay? Same. Okay, and then you got Zi, Wj, and then -1. Oh, I didn't call it -1, I called it epsilon I/j. And then eta to the I/j. And then what you can do then is rewrite this as a sum over q equals 0 to infinity. Sum over k and the q index. I don't know why I wrote this out. I'm sorry, you guys. I'll get a clue eventually here. ZW, k index, and then Grassmann generator. K like that. Now this thing here is a funny thing. This is either 0, 1, or -1, depending on what the I and the j look like. It's 0 if when you reshuffle the indices, if there are any repeats in the multi-index I and the multi-index j, it's 0. If I and j are already in order, if they're already like just 1, 2, 3, 4, 5, 6, 7, a billion, 1, a billion 2, a billion 3, then you're done. It's just 1. But more generally, it's a product of the number. It's -1 to the power of the number of transpositions it takes to reorder the indices such it's increasing. So the question is how many reshuffles, how many transpositions you need to do that. Oh, sorry. Okay. It's probably helpful if I don't think it matters that much. Let me just do one just for the sake of making sure I'm not just talking past you. If I had eta, let's say 1, 3, and then I had eta 2, 4, like that, well this would mean eta 1, eta 3, eta 2, eta 4, and so in order to put it in order, I'd have to do eta 1, eta 2, eta 3, eta 4. That generates a -1 because I had to flip the 3 and the 2. And so this would tell me that epsilon of like 1, 3 / 2, 4 is equal to -1.
More similarities to my one.
And this is slightly confusing notation because this is actually, in this notation, this symbol is actually meaning what? I mean, I write this here, that's an increasing index, is my point. So it's the same indices, but they've actually been rewritten. I mean, that's another subtlety of this notation. All right, anyway, enough about that. Oh, goodness gracious. Let me try to pick up the pace in here a little bit, if I can. So the next thing is to define a norm. Oh man, really? Oh, I know so late. Golly, that's a drag. So the norm of z is going to just be the sum p equals 0 to infinity of the sum I and p indices of the modulus, or, well, yeah, I'm really mostly interested in the case that Zi is an element of the complexes, all right? So that's going to be the norm. of a supernumber. So it's some kind of, for me it's a kind of a mixture of, I mean, okay, so the modulus in some sense is the 2 norm at the level of components, right? Which is convenient to me for various reality conditions in terms of how the modulus interacts with conjugation and such. But then, you know, this is a marker I should throw out. Oops, sorry. So that's that. What are its properties? Oh, by the way, now I can define the set of supernumbers I actually like to work with. So lambda is defined to be z in lambda infinity algebra. I'm now going to admit to you that I actually allowed for infinitely many terms to be non-zero. Or I don't see. I'm a little rusty here. I don't remember what I did. Well, I'd have to read this more carefully than I am, right? There's 2 different ways I could think to go here. The one way I could think to go would be to let lambda algebra infinity be the space of like polynomial Grassmann numbers, right? And then this wouldn't be quite it. This isn't really quite what I think of as supernumbers. It's more than just those polynomials that are finite. I mean, that would actually already be this would be a trivial thing to write. I mean, that's already true if these are just polynomials, because it's always just finitely many non-zero things. So what I really mean by this is as many things can be non-zero as you like, and we're just not worrying about convergence. But another way you could think about this would be take the polynomials and look at its closure. Take sequences of polynomials, then you'd get that. But I have a proof here that lambda is complete. Anyway, so anyway, this is the supernumbers. Basically, infinite sums of possibly infinite sums of Grassmann generators with complex coefficients, such that this norm is finite. Properties of the norm, some of them you will recognize. Non-negative. It's positive definite. It is got the triangle inequality. Right? And you even have homogeneity like this. And here I'm just, now this is for z and lambda and alpha in the complexes, okay? We don't have multiplicativity of the norm with respect to the supernumber multiplication. It is not in fact true that the norm of a z supernumber z times a supernumber w, that's not just going to be equal to norm z times norm w, but we do have this. So it's like the complex modulus, but not entirely the same. In summary, what this means is that lambda forms a Banach algebra. Because you can also show, in fact, you can prove that it's complete. You can look at a Cauchy sequence of supernumbers that converges. Excuse me. You can take a Cauchy sequence of supernumbers and prove that it in fact converges to another supernumber of finite norm. The proof of that is about a page and a half. So I will skip it. and tell you some technical properties of supernumbers. Before I do that, you guys have any questions? Let's see here. All right, yeah, let me just keep at it. I want to skip ahead and tell you interesting stuff, but I must resist the temptation to do such, because these things actually do matter. Cancellation property. Grassmann generators, squaring to 0 is treacherous. But even so, we have the following. If you have U, W, and Z supernumbers, all right, and I get confused between the statement and the proof. And if AZ is equal to AW for all A in that, then Z equals to W.
Is that a 1?
That is a 1. And it is on purpose on that side. So, how can I say this? Notation ZP is an element of lambda P. So these are the degree, the Grassmann degree of ZP is just equal to P. These are just one Grassmann generator. More to the point, what you usually do is look at all Grassmann generators. I mean, for example, eta I is an element of this for all I. More to the point. Now, of course, what do we have? If you have AZ is equal to AW implies Z equals to W, that is entirely equivalent to what? AZ minus AW, which by the way is A times Z minus W equals to 0, implies that Z minus W is equal to 0. So instead of proving the cancellation property, we can try to prove, so we'll try to do what? We'll try to show that AZ equals to 0 for all Z in degree 1 supernumbers. That implies that Z is equal to 0. If we can do that, then we've got the cancellation property by what's just above here. All right. It's been a while. Let me see if I can do it. So, let's see here. So we have that A times Z is equal to 0 for all Z in these supernumbers, right? So in particular, we can expand this A. A is really what? A is the sum. K equals 0 to infinity, right? Of A sub I, well, excuse me, my other sum. Sum I element of IK, right? Of A sub I, A to I.